Okay, welcome. This is Dr. Morton, and so I'm going to cover. This is continuing review for for the first test, which covers chapters 1 to 5. And I'm going to do a couple things. Usually, I have you do a practice test, and so we'll get to that in a minute. But first, I want to do some practice POS to SOP, kind of some level 1 things. And before we do that, we'll just kind of go over the syllabus real briefly here. So let's see. So here's the syllabus, and you can see that. So here we are on class 9. So we have at 11:59 tonight we have homework 4 is due. I might hit a homework problem or so. We'll see, and then. Then next Saturday, quiz for chapter 5 on the 17th. So don't forget that, but that's coming up. And then we also have the chapter 5 homework due on the 16th, which is Friday. Okay. All right. And so what we're covering, we're just doing the review. So I won't go all the way back up here and do that. Okay. And then, so that's the syllabus. Okay, so here are the problems I want to go through. I'm going to do these one at a time, and I'll just put these down a little bit. Yeah, hopefully this will be good, pretty good. Okay, there we go. Okay, now, so let me transition to, so I'm going to do the first one. So we're just going to go through these. The first one, A plus B quantity times A prime plus C. All right, so you might suspect that this is a multiplying and factoring, and you'd be correct. So let's look at that. We'll switch over here. So A plus B quantity times A prime plus C. All right, so remember the multiplying and factoring, which is X plus y quantity times x prime plus z equals, and we do this little business here where we do this, and we get xz plus x prime y. All right, and we're applying it in this direction because we're going from POS to SOP. All right, so applying this, all we have to do then is we draw our little thingies, and that should give us AC plus A prime B. All right, so pretty easy. All right, let's look at the next one. So the next one is A B prime quantity times A plus C primes times quantity A plus D. All right, let's write that down, and we'll think about how to do that. So it's A plus B prime, and then quantity A plus C prime, then quantity plus A plus D. Okay, so here we go. So A plus B prime, quantity times A plus C prime, times quantity A plus D. Now, remember our second distributive law, conversion theorem 2, C2, which is, and we had a corollary to that. The corollary was x plus w y z equals quantity x plus w times the quantity x plus y times the quantity x plus z. We kind of have something that looks like that, don't we? We have an a in each term, and then we have this other variable. So all we have to do is write a plus B prime, C prime, D. Done. All right, let's look at the next one. So now we have the quantity A plus B prime plus C, quantity times A plus C prime plus D times the quantity A plus C. All right, let's look at that. So we have let's see, A plus B prime plus C, quantity times A plus C prime plus D, a plus c prime plus d times a plus c. Now, the first thing we should think about is using our simplification theorem, and I believe it's S3, which is x plus y quantity times x equals x. So we can just drop that term. Well, in this case, we can let a plus c be x, and here we have a plus c here plus b prime. We can rewrite that a plus c plus b prime. So because of this term, we have x plus y, and here we just have x. We can drop this whole term. And then that just leaves us with a plus c prime plus d. Now, because of S2, where we have x times x prime plus y, and we can drop the x prime, and just equals xy. In this case, we can drop this c prime, and that just leaves us a plus d quantity times a plus c, and that's just now we use conversion 2 again, which not the corollary here, just x plus wy equals x plus y, or well, which is x plus yz equals x plus y quantity times x plus z. And so we have an a will be our x, and d and c, so that's just going to equal a plus cd. All right, and then let's do the next one. So we have a plus c, a plus d prime, b plus c, and b plus d prime. So let's see what we have here. So what can we do here? Well, let's write this down and let's think about it. So now we'll flip this upside down, and we'll do so that was a plus c, a plus d prime, b plus c, and b plus d prime. Now, you probably can't look at this and see where it's going, so let's just go ahead. We know what we can do with this, a plus c and a plus d prime, so we can, this part here, we can just turn it into a plus c d prime quantity times, and here we can just do b plus c d prime. Now we have x, and this is y, and this is z. So then we can just write that c d prime plus a b. And now it's in SOP form. And here it's in POS. And here it's in mixed. All right? And finally, let's look at the last one. A plus c quantity times a plus d times quantity b plus c times quantity b plus d times a d prime. All right, so it's basically what we just had, only we're multiplying it. So let's switch it here. So it's this right here plus a d prime. Well, our a lets us drop these two terms. Our d prime lets us drop this term. And so then we're left with, I guess we did that right. Yeah, AD prime. Yeah. So then we're left with b plus c times AD prime. And that's just going to be AB d prime plus AC d prime. And I just wrote it alphabetically here. Okay? That should do it. And that's now in SOP form. This is in mixed form. Well, actually, this is actually in POS. That's fine. It's not in mixed. It's POS. These are just single variables. Okay. So, okay, so that kind of covers what I wanted to cover. And with that, let me now just, I want to switch to, let's see, I want to, hang on a second here. So I want to switch to this practice test. And so I believe this is on the web. Let me just verify that. I'll have you pull it off of Blackboard, but hold on. Okay, so we're going to do a practice test now. Now here's what I suggest. I'm going to work through the test. I suggest you download the test off Blackboard, and let me show you where it is. Here's Blackboard, and if we scroll down all the way to the bottom, there it is. Practice test 1, F22 from F18. And if we open it up, here's what it looks like, and we'll just go ahead and expand it. Okay, so I'm going to work through it, and hopefully you'll be happy with that. Okay, so I suggest you stop the video now, and then once you've worked through the test, then turn it back on here at 11 minutes and 21 seconds, and then watch me work through this test. And that's what I'm going to do now. If you want to watch it, that's fine, but you'll get more out of it if you try and work it first. All right, so I'm gonna, I think I printed this out, so let me do that, and I'm gonna work through it. Okay, hang on. Okay, so here we go. So the first problem, you're designing a system to test compasses by putting them in a magnetic field and measuring how the needle points. You stick an optical shaft encoder target onto the compass needle and then measure the angle it points with a shaft encoder that is positioned over the compass. The sensor must be able to read the angle over 180 degrees in 10-degree increments. So answer all these questions. Okay, so here are the questions to answer. So first off, let me show you kind of what we're doing here. So we have a compass, and we've got a say a needle. And we're going to stick a shaft encoder on the needle like that, and it's got all these bands, and it allows us to read the angle that the needle is pointing to within some degree of accuracy. So here's the question. So the sensor must be able to read the angle over 180 degrees in 10-degree increments. All right, so that would be 18 degrees. I mean, sorry, that would be, so 180 divided by 10, that gives us 18. So there's 18 10-degree chunks, but remember, when you draw the line, you have to have the beginning of the line and the end of the line, plus all these points in between. And that the fact that you have to have the beginning and the end means you actually have 19 points. So just keep that in mind, not 18. So now we need to read it. But it's only over 180 degrees. Okay, so we have to have at least 19 bins. So if we have 19 bins, how many bits is that going to be? Well, here we could take the log base 2 of 19 and round up to the nearest integer, but it's easier just to know the powers of 2. So the powers are 2, 4, 8, 16, 32. So we have to use 32 because 16 is less than 19, and if you round up to the nearest power of 2, it's going to be 32, and that is 2 to the 1, 2, 3, 4, 5. So 2 to the 5th. So that means we need 5 bands in our target. So how many different things must you be able to represent with your digital value? Well, we have to represent 19 things, because that's the number of angles to get 10%. To get 10 degrees from say 0 to 180. Okay, how many bands must the shaft encoder have to get this accuracy? Well, so we have to go to 32, the nearest power of 2, bigger than 19, and that's 5 bits. So we need 5 bits. Is the shaft encoder, or 5, and we get 1 bit for each band on the shaft encoder, so that's 5 bands. Is the shaft encoder considered analog or digital? It is one of the few true digital sensors. what kind of code should be used in the shaft encoder to avoid big errors? Well, we've talked about this. We have to use a gray code. And the reason for that is when the shaft encoder changes, and let me go to the book and I'll show you a shaft encoder. Okay, so if you go to the book to figure 310, you see a shaft encoder. Now this is a great example. This one has 1, 2, 3 bands. We actually need one with 5 bands. But this is a poorly laid out one, and this explains why you have to have a gray code. Okay, and the reason you have to have a gray code is because if you have all 3 transitions, like in this case, we go from black to white, black to white, black to white. All 3 bands transition on this line. Over here, all 3 bands transition here too. Black to white, and white to black. Here, only 1 band transitions from black to white. This stays white, white, this stays black, black. Here, we have 2 bands transitioning, this from white to black, this from black to white, but this one stays black. So at some places we have 2 bands transitioning, some places we have 1 band, and some places we have 3 bands transitioning. The problem is if you let more than 1 band transition at any one of these interfaces, and there's 1, 2, 3, 4, 5, 6, 7, 8 interfaces, whatever band is transitioning at exactly this interface, the photocell will be over it, and it's going to read here, it's going to read halfway between black and white, so it's going to get a number, and we're not sure whether that number is going to threshold and trigger into saying it's black, or whether it's going to go the other way and say it's white. So we know when they're all lined up like this, they will have some uncertainty on this band, we'll have a little bit of uncertainty on this band, and a little bit of uncertainty on this band. What happens is then, this band could change first, so when you're right on this interface, you could have black, you could have say 0, 1, 0, or maybe this one would transition and these wouldn't, so you could have a 0, you could have 0, 1, 1, or basically it turns out you could have any possible value of the 8 possible values that 3 bits give you. Any of those values are possible because you have uncertainty in every single bit, and that means you have right at that transition complete uncertainty at what it'll read. So it could read anything, and what that means is it could tell you at that instant that it's in any one of these sectors. You actually don't know where you are when you're in that transition, so you have complete uncertainty. Now if you're back here, yeah, fine, you know you're here, and here you know you're here, but when you're right on that line, you don't know where you are, which means at any given moment you're looking at just the information coming off the photocells, and you don't know where you are, so you have enough uncertainty to invalidate any reading. And that's the reason why we we only allow 1 bit to change, so we only have uncertainty plus or minus 1 bit. Now the problem is you can't make these numerically so that you can compute what band you're in. You have to have a lookup table. So you have to have a lookup table that says which band you're actually in. But that's how the gray code works on a shaft encoder. The gray code only changes a single bit at every interface. And so that's what we need. That's what we need. All right, so all right, okay, so back to the test. All right, so let's go here, and so because of that, we need a gray code. If the optical target is stuck on 3 degrees off, does this affect precision, accuracy, or both? Well, it affects precision. I'm sorry, that was wrong. It affects accuracy. We can read it as precisely as we ever could. It's just that we'll be off by 3 degrees, which means it's our accuracy. So we can read it very accurately, very precisely rather, but our accuracy is off. It doesn't affect both. It does not affect the precision. We can still read it as precisely as we always could, but now the value is just 3 degrees off. So it's accuracy that it affects it. Okay, I'm not going to do this math because you guys can use calculators, so I don't want to spend any time on that. I do want to point out 2 things though. We'll do this little subtraction. I want you to use the method I teach in the book, and that is you just write the figure 2. So 0 from 1 is 1. 1 from 0, can't do that. So we borrow this 1. That leaves us a 0 here and a 2 here. 1 from 2 is 1. 1 from 0, can't do that. So we put a 0 up here and a 2 here. 1 from 2 is 1, decimal point. Now we want to take 1 from 0, can't do that. So we borrow this. We got a 0 here now and a 2 here. But we want to borrow 1 from that 2, so that leaves us a 1 and a 2 here. And then we borrow from that. It's a 1 and a 2 here. And then we take 1 from that 2 and we get a 1. We take 1 from that 1 and we get a 0. We take 0 from that 1 and we get a 1. We take 1 from this 0, can't do it, so we borrow that, have a 0 there and a 2 there. 1 from 2 is 1. So our answer is 1, 1, 1, 0, 1, 1, 1, 1. And the decimal point is right there. All right, so that's a good way to do it. We've talked about multiplication. You just, if your multiplier is a 1, you copy this. If it's a 0, you just copy zeros and shift. So this would be 1, 0, 0, 1, 1. And then here we copy a 0, 0, 0, 0, 0. And here we copy zeros again. And then finally we copy 1, 0, 0, 1, 1. And then you add up all these. And that gives you your answer. All right, and it would be 1, 0, 0, 1. Oh no, sorry. 1 plus 1 is 0, carrier 1. 1 plus 1 is 0, carrier 1. 1 and 1 and 1. So it's 1, 1, 1, 0, 0, 0, 0, 1. Okay, pretty sure that's right. All right, 2's complement. So we want to convert 49 to a 2's complement. So 49 divided by 2 is going to be 24, remainder 1. 2 into 24 is 12, remainder 0. 2 into 12 is 6, remainder 0. 2 into 6 is 3, remainder 0. 2 into 3 is 1, remainder 1. And 2 into 1 is 0, remainder 1. So remember, this is our low order bit here. Sorry. That's our low order bit. So we're going to write 1, 0, 0, 0, 1, 1. Let's check it. So this is 1, 2, 4, 8, 16, and 32. So 16 and 32, so that's 48, 49. So that checks, 49. All right, now we want to convert this to a 2's complement in 8 bits. Notice we only have 6 bits here, and this is supposed to be a positive number, but our higher order bit's a 1, which means in 2's complement that's not going to work. So we have to pad it out to 8 bits. Now these are zeros, which means this is positive 49. We want to make it minus 49. We take the 2's complement, and the way we do that is we invert every bit and add 1. Or you copy bits till you get the first one, copy that, and flip every other bit. So in this case, we just write down the 1, and then we'd flip all these 1, 1, 1, 0, 0, 1, 1. Now our higher order bit's a 1, which means it's negative, and this equals minus 49. All right, okie doke. So here we're gonna prove this theorem. So the way we do this, so the theorem is y prime plus z prime, quantity times x prime plus y, equals x prime y prime plus y z prime. Yeah, so that's basically the multiplying and factoring theorem. All right, so let's see, and let's see if there was a typo here, because I think there might have been. Y prime z prime, that's good. X prime y, that's good. X prime y prime, that's good. Y z prime, that's good. Y prime z prime, that's good. X prime y, that's good. X prime y prime, and y z prime. Okay, they all look good. Okay, so let's just do these columns, and then we'll see if these final two are exactly equal. So y prime or z prime. So y prime, 0 means it's a 1. So yeah, so that's a 1. That's a 1. Because the z is a 0, that's a 1. And then we repeat it, that's a 0. So 1, 1, 1, 0. How about x prime y? So we have 1, 1, 1, 1, because we have 4 zeros for x, and that's x prime. And y, we have 0, 0, 1, 1. And now we have x prime and y prime, x prime and y prime. So that would be 1, 1, 1, 1, because they're primes. Then anywhere we have a 1, we're done, and so all the rest of these are going to be 0. And then y and z prime. So y and z prime. So z prime has to be a 0, y has to be a 1. So when we have 1, 0, it's going to be a 1. And 1, 0, it's going to be a 1. And all the rest of these are going to be zeros. Okay? And then, now we can combine, we can group them up. So here we have to AND these. So 1 and 1 is 1. 1 and 1 is 1. 1 and 1 is 1. 0 and 1 is 0. 0 and 1 is 0. 0 and 1 is 0. 1 and 1 is 1, and 0 and 1 is 0. And then here, if either one of these are 1, we're good because we're ORing these two together. So 1 OR 0 is 1. 1 OR 0 is 1. 0 OR 1 is 1. 0 OR 0 is 0. 0 OR 0 is 0. 0 OR 0 is 0. 1 OR 0 or 0 or 1 is 1. And 0 0 is 0. Notice these exactly match. So that proves left equals right for all values of x, y, and z. All right. Let me do the next page. By the way, the test won't, it's not, well, it's going to be online. It'll be totally different than this, but this is just to give you a little bit of a feel. All right. Here we go. Right there, I think. Okay. Use De Morgan's laws and convert this. I don't think I've covered Morgan's laws yet. So all De Morgan's laws are you change all the variables by flipping them from prime to non-prime or prime to or non-prime to prime, and then you flip all the all the operators, the ands, the ors, and the ors, the ands, and you make sure you use parentheses to preserve the precedence. And if you do all that, you'll be fine. Here we have x and y inverted. So that's just going to be x prime or y prime. Here we have x or y. So that's just going to be x prime, y prime. Remember, they have to be ANDed because they're ORed here. These have to be ORed because they're ANDed here. And then we have this expression. So what we want to do, we want to go ahead and put parentheses around this so we can keep this separate. So now we're going to invert everything. So we'll put a tick here. We'll put a tick here. We'll take away the tick there, and we'll change these out to multiply. So that'll give us w prime x quantity prime times y prime z. And then we're going to take this prime in here, and we're going to get w plus x prime quantity times y prime z. So you can see we really had to put these parentheses, otherwise we would have made a mistake. All right. Let's look at this. Multiply out to SOP and show work. Okay, so A plus B, B plus C, B plus D. So you notice there's a B in every term. It's like the second distributive law we just looked at. X plus W, Y, Z equals quantity X plus W times X plus Y times X plus Z, where the B is the X in this case. So that's just going to be B plus A, C, D. Okay, draw the logic diagram for this expression. So it's a bunch of OR gates. It's 1, 2, 3 OR gates going into one final AND gate. So we'll just do these like this. I'm almost making them look like exclusive ORs, but they're not. And then these go all into the final AND gate. And that's F. And that's all you have to do. It's Z and X going in here, Y and X going in here, and W and Z going in there. You don't have to simplify this or anything. You just have to draw the circuit. Convert. Now, let's see. Convert this into POS form. So it's currently in SOP. We want to go to POS. So we have a B prime C here, a B prime C there. Well, that's redundant, so we just get rid of that. And we have a B prime C here, so we can get rid of that term. And now we're just left with A, B prime, C prime, plus B prime, C prime. Well, we can get rid of this term too. So now we're just left with B prime, C prime, which actually is in SOP or POS. You can consider that either form because it's just two individual variables. So everything drops. I made a mistake. I shouldn't have crossed out this one. So let's go back and fix this. What I should have had is this one out and this one not. So let me rewrite that. So we should have had A prime, B prime, C plus B prime, C prime. Now the one thing we can do, we can drop the C because of our simplification theorem. I believe it's S2, which is X Y X prime Y plus X equals Y plus X. Okay, so we can drop this variable, where the Y would be the AB prime. All right, and so then once we do that, now we just have A prime B prime plus B prime C prime. We can pull out the B prime times A prime plus C prime. And now that's in POS form. That's the first distributive law. Or C1. Okay, answer the following questions. Okay, the ASCII character, yeah, we're good. You can see the whole thing. The ASCII character B and the standard font for B both take 1 byte. So you know, because you looked up about glyphs, you know that these fonts actually have a bunch of glyphs. They take lots and lots of bytes, not a single byte. So it is false. The ASCII value is 7 bits, but the font is many bytes. So it's false. Years ago, with noisy phone lines, what codes was used to help reduce errors in transmissions? We used the parity. And I talked about this in class. We should try to eliminate ambiguities around the videos. We should try to eliminate ambiguities even though the logic is the same. True. What is the output for a 3-input exclusive OR gate when the inputs are 0, 1, 0? The output equals 1. Write a Boolean equation for this sentence. All right, so I'll do this quickly. So W, yeah, this was screwed up. It should have been, so it should have been hits, walks, so that should have been defense, great pitching, so it should have been H, W, D, P. So it should have been H, W, D, P, and we'll say that equals, so I'm just going to write it one way. That's really all I care about. Well, maybe I'll write it 2 ways. So, okay, so the Cubs will win the World Series if they get big hits or lots of walks and play good defense or have great pitching. So lots of hits, walks and defense, pitching. So that's not bad, but you can also say hits. You could say hits and walks and play good defense. That would be another way to look at it. Because if you just get hits, well, if you just get walks and defense, you might not get any runs. Because it takes a lot of walks to get walked into home, enough to win the game. So that might make more sense. So there's a couple of different ways you can do it. All right. Next. All right. This one is really a little bit tricky, and it's easy to mess this up. So first off, when I evaluate this, so if I put an A in here, I get an A prime here. So if A is a 1, this will be a 0. And if B is a 1, this will be a 1. If C is a 1, this will be a 0. And then if I get a 1 here before the bubble, I get a 0 after the bubble. All right, so what I'm looking for then, you remember in the OR gate, so the thing that's going to be unique, if any of these inputs are 1, I'm going to get a 1 here and a 0 out. So I'm going to have lots of zeros, but I'm only going to have one combination that's going to give me a 1. And that combination is going to be when all the values going in are zeros. So what would it take to get 3 zeros going in? Well, the A would have to be 1, the B would have to be 0, and the C would have to be 1. So A is 1, B is 0, C is 1. So right here. So in this one, I'll get a 0 before the bubble, and I'll get a 1 after. But everything else, I'm going to have at least 1 here, so I'll get a 1 before and a 0 out. So for this row, I'm going to get a 1, but for all the other rows, I'm going to get a 0. And if I do the minterm solution, I just need this. Which row is this? That's row 5. 0, 1, 2, 3, 4, 5. So that's minterm 5. And that's all there is to it. If POS switched to SOP and vice versa. So let's go through these. We'll see if we can make sense out of that. And hopefully, yeah, you could see all that. Yeah, I think so. All right. So here we have an A. So we can get rid of this, and we're just left with A times B plus C. And we just use the first distributive law, and that gives us AB plus AC. We just distribute the A in. Now it's in SOP form. All right, here we have WXYZ. We've looked at this before. We're just going to use W plus XYZ equals W plus X, W plus Y, W plus Z. And so in this case we have primes, so it's going to be W plus X prime, W plus Y, and W plus Z prime. So that's the answer right there. Okay, and here we have an A and an A prime, so that's easy. We're going to do the M and F. So that's going to be A prime plus C quantity times A plus B. All right, so those are pretty easy. And then finally, this last page. So we have a truth table here, and we want to we have one don't care, and we want to see what's the best simplest form. So we're going to have to solve it two ways. One where x is 0 and one where x equals 1. This x. All right. So let's first do the 0. So we're going to take minterm 0. 1, 2, 3, minterm 0, 3, 6, and 7. Okay, so minterm 0 is just going to be A prime, B prime, C prime. Minterm 3 is just going to be A prime, B, C. Minterm 6 is going to be A, B, C prime. And minterm 7, A, B, C. We can combine these, we get A, B. We can't combine... Yeah, we can't combine these, but we can combine this and this one and get BC, and then this one we have to just bring down. So that final solution is going to be A prime, B prime, C prime, plus BC plus AB. We use this term twice, and that's totally legal. And then let it equal 1. We're going to add to that then the term here for the don't care, which is going to be A prime, B, C prime, A prime, B, C prime, plus A prime, B prime, C prime, plus these, which we already reduced to BC plus AB. So we can combine these two, and we'll get the B drops, so we're going to get A prime, C prime. Yeah. And can we do anything else with that? Not really. We're pretty much done. Okay, so then we get A prime C prime plus BC plus AB. So that's one answer, and this is the other answer. You can see this answer as an extra variable in this term, so this would be simpler. So we want to choose x equals to 1. So we pick a 1 for the don't care. Now this final thing, I can't remember if we talked about this or not. But here you have a 4-bit adder, okay? you have 4 bits of A, 4 bits of B, 1 bit of carry in, 4 bits of sum, and 1 bit of carry out. So you have 1, 2, 3, 4 bits of A, 1, 2, 3, 4 bits of B, a carry in, and then you have 5 outputs, carry out and 4 bits of sum. So you have 9 inputs. That means 2 to the 9th rows are 512 rows. And here are a couple of rows. Now, all you have to do to solve these is you just have to add these up. So we'll take the first row, and we have, so we have B is 1100. Okay, and then we have a carry in. So then we just add these. 0 plus 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carrier 1. Or 1 plus 1 plus 1 is, I didn't do that right. 1 plus 1 is 0, carrier 1. 1 plus 1 plus 1 is 1, carrier 1. All right, so we have 1, 1, 0, 1, 1. So our carry out is a 1, and our sum is 1, 0, 1, 1. Let's do these. So we have four zeros for A. So we'll move those over here for B. And then we'll put the carry in, which happens to be a 0, so we don't even need it. So that's another 0. Okay, so 1 plus 0 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 0 is 0. There's no carry out. So 0 for the carry out. 0, 1, 0, 1. So that's pretty much it. Now, if we wanted to convert the B subtract B from A, all we have to do is we just have to put bubbles on all the B inputs, or an inverter, if you will, and then put a 1 into the carry in. And that'll turn B into a minus 2's complement number, assuming it'll fit in 4 bits. And we'll effectively subtract it from A, and we'll put the sum here and the carry out there. And in the case of 2's complement, we ignore the carry out, and that's all there is. So you can use 2's complement. So the best way to turn this adder into a subtractor is to use 2's complement, put a 1 into carry in, invert B, and ignore the carry out. Those are all the good choices. All right, so that's it. Now this is definitely a little bit harder test than you guys are going to get. So don't freak. And some of these things, so we'll cover more of these things. I'll work through some more stuff next week. Let me do the full screen. Yeah. Okay. So that's the test, and hopefully now you feel you've had a chance to look at it. You've gotten some experience working through it. If you struggle with stuff, just go back and review it, and we'll do. So I'm debating about. So why don't you email me and let me know if you want to have a in-class session on Wednesday, or if you want me to do a video. So just let me know, and I'll do whatever the preponderance of email responses is. Remember, send it to the paul.morton@utsa.edu, and then I'll just go according to your vote. All right. Talk to you later. Make sure you get your homework turned in by midnight.